presentation today is about on a tool we developed while I was working as a research fellow at the University of Auckland. It was focusing on the biodiversity management data, how we can provide a secure solution for that. The work was funded by the Maori community. That's therefore tēnā koutou katoa. I'd like to acknowledge the tangata wenua, the people of the land. Without their support and funding, this research would not have been possible. Thank you so much. Right, so kauri dieback. Kauri dieback is a disease which affects the kauri tree. It forms molds, as you can see. It spreads easily. The challenge is it spreads easily. If you are walking, it can the soil pathogens, they can attach to your shoes and they can spread from one place to another. The Mataranga Maori framework for surveillance, they wanted to promote Indigenous people's control over their data. They wanted to provide they wanted a framework, they wanted an infrastructure where the Maori people could share data which concerns them, but at the same time it should be tied down to the location of the data, the place of origin. So as you can see in the diagram, as of 2020, these are the locations where they have found kauri dieback, the trees which have been infected. So for a framework to be built, the requirements were data should be linked to the place of origin, which also should accommodate various trust levels, meaning that only this intended biodiversity management area, the guardians of the particular biodiversity management area should have access to data if an infected tree was found in that area. Every other entity concerned in the system, they should have access to an approximate location of the data. Finally, they wanted to deploy this solution over the cloud. So how do we handle that? We have to ensure that whoever is the cloud service provider, they don't have access to the data set while it's stored on the cloud and also while in transit. And so we came up with a solution where the first point was every BMA user, they should have create a public-private key pair. I'm going directly into the technical solution. First of all, everyone concerned with the system, the researchers, the person uploading the data set, the data custodian, and the people concerned, the researchers, they should first create a public-private key pair. Then comes the safeguarding options. First of all, we perform geomasking. The geomasking option, first, it allows an anonymized version of the data set to be available to everyone concerned, right? While the original is encrypted and available only to the people guarding the BMAs, the biodiversity management areas. The hash value of the encrypted file gets stored on the blockchain. So whenever someone is trying to access the encrypted data set, first the data set gets verified if it's the original. We just want to ensure while stored on the cloud, it has not been tampered with, a way to verify the originality of the data set. Right, so the people, when they want to, the biodiversity management area, when they log into the system, first of all, they verify the data set based on the hash value stored on the blockchain, then decrypt, and then they can view the data set. Right, so we are using for public-private key pair generation, we are using a JavaScript library called browser PGP. You can actually download the entire library onto your machine and create the public-private key pair from that. And also there is a small option where you could use a passphrase. The passphrase encrypts the private key. Right, so first step, after creating the public-private key pair, we perform anonymization. So we give the user, the data guardian who uploads the data set, whoever collects, when they connect to GeoNode based on the cloud, before the data set gets transferred to the cloud within GeoNode, we perform geomasking. So we give them the option of minimum and maximum distance. This is the buffer within which they can displace the location point, the location data set, the location point, you can see. Right? And we have added a privacy rating. Privacy rating is basically a measure which ensures that the original, for each masked location, is it closer to its original location? If it is, then it's penalized, because the masked point, the masked location of each original point should be closer to any other original point. So yeah, second step, we perform encryption. Now encryption, we are using public key encryption. So the main criteria was every BMA area, whoever is the data guardian of the BMA areas, biodiversity management areas, wherever the points fall, they should have access to the entire data set. Now if you can see in the map, the original points, they fall, the original points in red, they fall in 3 locations, BMA, right? BMA is 33, 34 and 6. So all those 3 BMAs, public key is used to encrypt the data set, this map. And then on the right, if you see, we have Ember. She is a researcher. So in addition to the 3 BMAs, we add another user, and all these 4 users, public key, are used to encrypt the data set. Once done, that is encrypted and stored on the cloud. Finally, the hash value is used. The hash value of the encrypted data set is notarized on the blockchain. In this case, we use the Sepolia testnet, and we post the hash value. So there is a minting server that will run in the background. This hash value will be minted on a central Ethereum address, and we use an API to pass the hash value. The performance of the browser-based encryption is, we did not expect large data sets, so the encryption was actually very fast. Right, so let's cover the masking aspect first. So masking, geomasking is, the performance using the browser is 10,000 points per second. Right, so 10,000 points per second, that's actually very fast. But if you want to implement the privacy rating, Spruil's measure is the privacy rating we used. So if you want to use Spruil's measure as well, then it slows down to 440 points per second. Right, encryption is 3 megabytes per second, and decryption is 4 megabytes per second. That's fast. And yes. These are practical times for physical, practical implementation. Now I just want to quickly show this. Right. So this is the website, which is, so Stephen is the right. So first step is the public-private key pair generation. All right. Yeah, it's a long video. It's probably around 5 minutes. I will try and not show the whole video. Basically, all the steps, I cannot fast forward for some reason. Right, so what I will do is right, then I'm right, sorry about that. First is the public-private key pair generation. Then comes the main point where the user actually embeds their public keys into their profile within GeoNode. So GeoNode, the model was modified. The Django files were modified to accommodate the public key for the user. After that, the data sovereignty functions were enabled. The user can choose to enable or disable that. After that, the layer is uploaded, and then the geomasking is performed. Right, and then after that, the additional system users can be chosen, right? And then the encrypted layer is uploaded. Right, so two layers are being uploaded at the same time. One is the encrypted layer, which will be uploaded as a GeoNode document, and then the anonymized version will be uploaded as a GeoNode layer. Right. So you can see the locations which will be shown to everyone is actually the anonymized location. Right, the anonymized location, and then the users, when they log in. Right, so this is the user who is logging in, trying to view the data set. Privileged user, and they will only see, initially they will only see a masked anonymized version, and this is, if you go back, this if you see down there, the link to the blockchain address is shown, and that will contain the right. So that contains the URL where the hash value is notarized. On the right, you can see automatically using that address, the hash value is checked. The layer which is retrieved, the encrypted file which is retrieved from the cloud, its hash value is computed and compared with the hash value which is minted on the blockchain. If it corresponds, both are the same, then that green tick will be shown. The next step, once it's verified, the next step is to decrypt. So individual users, what they will do is enter their private keys to decrypt the data set. So here is the facility where they will upload their private keys. Everything is browser based, JavaScript based, so none of the private keys or any decrypted data set will be transferred from their machines. Right? Now, upon decryption, the original location of the infected trees will be shown. Right, so that was the a live demonstration. Right, so what are the advantages? So we were able to accommodate varied trust levels when they are in a system. When we needed users, when we needed to deploy this data set with different trust levels, we first of all perform geomasking. Then encryption, public-private key, we used to accommodate that prevented us from sharing the encryption key on another platform. Basically, symmetric key encryption, once you encrypt the data set, you'd have to share it, the key somewhere. But using public-private key encryption, we just use the public key of each of the users who wanted access to the system, to the data set. And that allowed us to accommodate that requirement. And then finally, to prove originality, we used the hash value was stored on the blockchain, right? And all this was is integrated as part of GeoNode that was cloud-based, right? So yes, there were some challenges as well as benefits. The challenges is the users, they have to be, once they lose their private key, that would have been that is a challenge. So safeguarding their private keys is essential. So the solution we came up with was, we store a backup of their private keys. We the system administrators can on their behalf store a copy of their private keys somewhere offline, but it would be protected using a passphrase. So the library we use, OpenPGP, that provides a facility where the private key can further be protected by a passphrase. So they keep their passphrases while we keep their private keys. So that was an option. Right. Another resource limitation would have been that if we use large data sets, and then whether browser-based encryption could support that. Right. But overall, we were able to accommodate, we were able to provide a trustless cloud-based solution for data sovereignty. At the same time, we were able to, by doing this, we were able to support security and accommodate the diverse stakeholders. Now, once we handed over the project, the tool which we developed, then we were aware that other communities, not only in New Zealand, other communities in Australia, indigenous communities can take advantage of this tool which we developed. So we had made it available on GitHub. So what are the list of changes which we need? But most of the changes were JavaScript changes, HTML file changes, and a little bit of changes into the Python files within the models, right? So yeah, so the main list of changes would be the layer upload and layer detail, a little bit of JavaScript files for geomasking and encryption, and then Python changes to the model, right, to store the public key and the notarization URL. Right. And finally, I'd like to thank the University of Auckland and the Manaki Land Care Research, Land Care Research, with whose support the project was undertaken. Thank you. Any questions?
Kia ora, really good stuff. I wanted to just ask if, say people have, say there's no a full zero trust system, is it possible to decrypt all of the data offline? Can you download the encrypted files, and can you upload only fully encrypted files?
Yes. So the encryption was done using browser PGP, or PGP basically, OpenPGP.
Yep.
So that was one of the questions our reviewers for the journal paper also asked. So there's a tool called Cleopatra, it's an encryption decryption tool. So once if a particular GeoNode user has access to the dataset, they can actually download the encrypted dataset and use Cleopatra, insert their private keys and decrypt it.
Mm-hmm. And can they also do that with the anonymized datasets? Can they anonymize it offline before uploading?
Yes, they can anonymize it offline. They can use we have another tool, mapsafe.xyz, or another which is based on another tool, maskmyxyz. So both are browser-based tools. They can anonymize it using that, and then I guess when they upload it onto this tool, it would be as the only layer. So if that's the only layer, then they can anonymize it offline and then upload it. Yes, they can use it.
Okay, great.
Thanks. It's a really interesting talk. So I may be misunderstanding this, but is the file or is the data stored at rest encrypted?
Yes. I think that the main gist of the research is that, and I forgot to mention, everything is done in the browser. Before it goes onto the cloud, all the security functions are performed within the browser using JavaScript. So the geomasking, the encryption, and the blockchain notarization, all that are executed within, from the JavaScript. So for notarization, we use Web3. For encryption, we use browser PGP. And for geomasking, we use maskmyxyz is another library. So the moment it's encrypted, then only the encrypted file is uploaded onto the GeoNode. And accompanying masked version, anonymized version, is also uploaded as a GeoNode layer. The encrypted version of the original dataset is stored as a GeoNode document.
Yep.
So that allowed us to store a encrypted version. So when it's in transit and while it's stored on the cloud, it's encrypted. Only that's the part of the, I guess, in the data sovereignty part, where the indigenous people or anyone using the system later on can control. So when if you see when they are trying to encrypt, they can choose, the individual BMIs are chosen, and then additional users can be chosen who can access the data set. So that's where the control part is. No third party is controlling that, the provision of security for them. They are in control.
Okay. One last question. Anyone? No? Okay. Thank you, Dr. Sharma.